Hello, so this video is about a really interesting property of the family of n equals 4 bicentric polygons. So what are bicentric polygons? You're looking at them here. They are these orange polygons that are interscribed, meaning simultaneously inscribed in an outer circle and circumscribed about an inner one. Now let OEXT denote the center of the outer circle, and OENT for internal, external. The OINT denotes the center of the inner circle. So I have this nice Poncelet family of quadrilaterals. Okay, and this family is known as a bicentric family, has been widely studied in the 1900s all the way up to, I would say, the first half and the 1960s of the 20th century. Okay, so I'm also showing here, so whenever you have 2 points in the plane, sorry, 2 circles in the plane, they're going to be associated with a pair of limiting points. Okay, they have special inversive properties. I'm going to leave some more information in the description. Okay, and I'm also showing here the midpoint between these two limiting points. It's right here because it's going to play an interesting role. Now, here's a point in the plane P0 that I can drag around. Okay, at will. I can place it anywhere. And I want to compute the pedal polygon of the instantaneous bicentric polygon with respect to P0. So let's actually do that. Here's a pedal polygon. What is a pedal polygon with respect to a particular point in the plane? I'm actually dropping perpendiculars from P0 onto the sides of my reference polygon. In this case, it's this orange polygon. You can see here that the feet of the perpendiculars are the vertices of my pedal polygon, and I'm showing these construction lines here, which represent perpendiculars dropped from P0 onto each one of the side lines or their extensions. Okay, so the cool thing is as I watch the dynamic geometry of my bicentric family, I can also watch the dynamic geometry of my pedal polygon, and for the purposes of this video, I'm interested in the area of my pedal polygon with respect to P0. This is a signed area since this polygon can become self-intersected, and I'm reporting the signed area here. You can see that it is a positive number. Okay, seems to be positive all the time, and it's variable. Okay, so if I change, for example, the position of P0 and I place it here, I get a different kind of varying area. Okay, so that's nothing too interesting. If I place it over here, I get a nice varying area. Now, as I move P0 towards the left, okay, there's going to be a point at which this area is going to become dynamically negative. So, for example, if P0 is over here, the area is dynamically negative, and it doesn't seem like my polygons or my pedal polygons are self-intersected anymore. So that's an interesting property. So it looks like, yeah, they're not self-intersecting, but the area is still -2 something. It's variable. If I go over here, the area is still negative, variable. If I go over here, all of a sudden now the area can become, or the polygon can become occasionally self-intersecting. My area is still negative. So it looks like if I cross the I think that there's something here where I crossed the L-mid vertical line. You know, this is just a hypothesis, but if P0 is to the right of a vertical line passing through L-mid, it looks like this polygon can become self-intersecting, but its area is still variable. Okay, but the main result in this video is the following. Let's now draw a vertical line through the second limiting point, the one that is external to the pair of circles. I'm going to draw a vertical line there. And I want to show you guys what happens if my P0 is to the left of this vertical line. It looks like my area, my signed area of my pedals is negative, and as I cross to the other side, my area becomes positive. Okay? So in fact, if P0, and this is the result, lies on anywhere on this vertical line, the area, the dynamic area of my pedal polygon is 0. Okay, so for example, now if I move P0 a little bit to the bottom here, and I place it exactly over this line, my signed area, the signed area of my pedal polygon with respect to these n equals 4 bicentrics is identically equal to 0 and invariant. So it's only on this line, okay, so this is one claim, where the area is invariant over the family, and it's actually invariant and equal to 0. With a special case, if P0 is exactly equal to the limiting point, so it's exactly on top of it, okay, I don't think I have a control to do that, this area is actually equal to 0, and my polygon is actually a degenerate polygon, where its 4 vertices are collinear. Okay, so what I can do here is I can actually draw a family of these polygons with 0 area. Let's actually turn off my my petal polygon. I'm going to draw a family of petal polygons. So here's a family of petal polygons with respect to a set of red points distributed over this vertical red line passing through the external limiting point. And as I animate the family, this whole family of petal polygons, each one of them is with respect to one of these red dots, right? So imagine that I'm displaying these anchor points here, these petal points, and I'm computing this whole family of petal polygons, each one of them with respect to a separate petal point. Since all these petal points lie on this vertical red line, each one of these petal polygons has individually 0 invariant area. Okay, so the way I showed this before was actually to do it manually, right? I could, let's turn these guys off, these 0 petal polygons off. I could go back to my generic petal polygon, and I'm reporting its area. And what I'm saying is that if the x component or the x coordinate of P0 lies on this red line, this family that I'm sweeping here manually of petal polygons with respect to P0 on this line, they all have 0 area. Of course, this is approximate because I'm having to draw this or to drag this with my mouse, but wherever I place P0, so if I place P0 exactly on the line, area is 0. If I'm over here and I place P0 exactly on the line, the area is 0, and the area is 0 dynamically. Okay, if I place P0 exactly on L2, let's try to do that. Now the area is 0 dynamically as well, and in this special case, and only in the special case where P0 is the second limiting point, my petal polygon becomes a degenerate polygon with 4 collinear vertices. So let's bring back the 0 polygon family to the screen. Let's look at it again. And of course we can also study the dance of a continuous family of 0 area petal polygons and ask questions as to, for example, are there loci of specific vertices? Are there coordinated properties amongst specific centers of these petal quadrilaterals, etc., etc., etc. Oh yeah, so one final claim is that the degenerate petal polygon will always intersect the line connecting the centers of the 2 bicentric circles at the midpoint of the limiting points. So you can see that dynamically, that guy over there, the degenerate one with respect to, so if I just draw it, I can just draw it, right? So I can just draw this guy here. It's a 0 area degenerate polygon with respect to the second limiting point, and it will always intersect the x-axis in this case, but in general, the line connecting the 2 centers at the midpoint of the 2 limiting points. Okay, hope you enjoyed this video. Thanks for your time, and I hope to see you on the next video. Bye.